Greetings, Math 111. We are in section 8.3, so this is the last section, news material, before exam 3. So hopefully you're kind of enjoying this section. I always do enjoy chapter 8 as well as chapter 7, but chapter 8 where we actually learn how to apply it. Today we're going to be talking about estimating P in the binomial distribution. So we've been estimating mu, so of course what is mu? Mu is the actual mean of the population. We use x bar, which is a sample mean. So you might expect, if we're gonna estimate P, remember that little p, because this is little p. So little p is the historical probability. So it's the real live probability, get my T crossed. It's the actual probability that we may or may not have a chance to actually understand what that is. So that's my actual probability. All right, let's jump in. All right, so we're gonna talk about, it's the same margin of error. Formulas look almost the same, again, but we're using P, so there's gonna be a slight difference. We're going to use, we're also gonna talk about how to estimate the sample size. We are going to use Z again. So we used Z in section 8.1 when sigma was known. We used T-chart when sigma was unknown, and now we're back to using Z when we're talking about the binomial distribution. All right. Binomial distribution, remember it's success and failure. Binomial means 2. So it's completely determined by the number of trials and the probability of success. If you'll think way back when we first started to learn about P, we had a wheel with 36 spots, and one of them was painted gold, and if you got the ball in that wheel, then you won whatever the big prize was. In general, we have to choose our number of trials in advance, and we also want to consider the problem of estimating P under the assumption that N is our how many are in the sample has already been selected. So when we were in section 8.1 and 8.2, we talked about N had to be greater than or equal to 30. Well, that may or may not work in this case. If we have a very, very small probability or a very, very large probability, because little p plus little q has to equal 1, right? What is little q? That's the probability of failure. So probability of failure is my little q. So those two things added together, often we think of it as little q is 1 minus p, right? That's just a little bit of algebraic manipulation. So, and I guarantee this is a test question. Ding, 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 test question. N times p is greater than 5, and N times q is greater than 5. So what does this mean? I have to have a sample size and a probability that when they're multiplied together gives me something bigger than 5. Again, that changes what's required of N. If P were tiny, 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 I'd need a bigger N. If Q were tiny, 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 I'd need a bigger N. So what this does is compensate for the fact that my sample size has to include information or has to be adjusted based on the probability. What if I had a bag of green M&Ms? It's springtime, so green M&Ms, and there was one yellow one in there, and I wanted to know what is the chance that when I take a handful of 5 M&Ms out that I'll get that one yellow M&M. Well, not very good if only one out of a whole bag. So that means I have to take a bigger sample size so that I might actually get that beautiful yellow M&M. Okay. We used X bar in when we were estimating mu. We are going to use P hat. So this little caret thing on top, P hat a point estimate for little p. Okay, so that's my point estimate for little p, and we will use that. It's R over N. What is R? R is the number of successes in this trial. Right? N is the number in my sample size. Remember that success is whatever we're looking for. Okay, in the flooded in the news is the COVID-19. Success might be that the person is sick, test positive on a test. That doesn't seem like a very successful thing, but if that's what you're looking for, then that's success. It also could be how many people pass away from a particular disease. Again, doesn't seem like true success, but when we're talking about statistical, success is just what I'm looking for. All right, so same relationship, Q hat is 1 minus P hat. So very similar. N is number of trials, R is number of successes. My mean, so mu of P hat is going to be just little p. That's the same piece of information. Sigma sub P hat, and this formula should look familiar from chapter 6, P times Q over N. All right, take the square root of that. That's my standard deviation. All right, let's get going. Our error formula. So we have the same kind of an error. My error formula is Z sub C times P times Q over N. Okay, so that's my error formula. Looks similar to the one we used when we're doing both T and Z with estimating mu, but slightly different. But we finish up in a very similar way. So this, we don't worry about the optional. I try to teach it just one way to keep everybody on the same page. Let me jump over that. But we use this same error formula that says, we'll get there, P hat minus the error is less than or equal to little p, which is less than or equal to P hat plus the error. I'm going to write down our formula, use a different color. If I had x bar minus the error less than or equal to mu, which is less than or equal to x bar plus the error. Do you see how those formulas are really similar? The difference is we're estimating p instead of mu, so we use p hat instead of x bar, but it's the same idea. One thing you should always remember is that probabilities are between 0 and 1, okay? They must be between 0 and 1. So if we're going to be between 0 and 1, these values of p hat have to be between 0 and 1, and my error is going to be small because it can't become negative and it can't become too large, can't be over 1. So these error numbers we'll calculate are going to be very small. All right, so we had a flu shot example a long time ago. Suppose that 800 students were selected at random from a student body of 20,000. So N is 800, so there's my N. And all 800 students were exposed to the flu. 600 of them did not get the flu. Let P represent the probability that the shot will be successful. So success is they don't get sick. So R is 600 for any single student selected at random from the population of 200. All right, N is my 800, that's my number of trials. R is how many didn't get sick. So let's do my estimate. So P hat is 600 over 800, which is 0.75. That means that Q hat is, whoops, I went too fast. Q hat is 1 minus the 0.75. So that's 0.25. That's my Q hat. Does it, remember we have to stop and ask ourselves, N times P and N times Q. And remember this is and, not or. Both of them have to follow this. Let me adjust this ever so slightly so you can see that screen maybe a little bit better. There we go. So my N is 800, my P is 0.75. So when I multiply those two numbers, I get 600. Oh, that's way bigger than 5. My N is 800, my Q is 0.25. When I multiply them, I get 200. Yes, that's bigger than 5. So this is a sufficient sample. I can use this process. This is legal, shall we say. And so yes, this approximation is appropriate. So we want a 99% confidence interval for P. Once again, I'm going to go to my Z-chart. On the back side where the positive values are is a little table in the lower left-hand corner. And when you look at that little table, you will see my confidence. So Z, so if, let's see, can you still see me? No, I gotta be over here. So Z of 0.99 is 2.58. Okay? Remember, we just used that value in our error calculation. So here's my formula. Error is Z for 0.99 for 99%. P times Q. Now this is just another way to write Q, right? 1 minus P hat. So P times Q over N, take the square root of the whole thing. So when I substitute values in, 2.58 times the square root of 0.75 times 0.25 over 800. Now don't forget calculator issues. Make sure you put this whole bottom, or this whole piece that's under the radical, make sure it has parentheses around it. So keep track of those calculator skills. And I come up with an error of 0.0395. Remember I said those errors are going to be small? Because I'm going to take my probability, which in this case was 0.75, add and subtract that piece. So let's see what that looks like. So I take my P hat minus my error, and my P hat plus my error. This is my confidence interval. So I encourage you on your formula sheet to have, make sure, it'll say that word on there, but you might want to write it up to the side. Say P hat minus the error and P hat plus the error is the confidence interval. So next to that formula, and next to the formula for estimating mu, write confidence interval. So how do I do that? So I have 0.75 minus 0.0395 is 0.71. And you're gonna ask, how much do I round? In a perfect world, you wouldn't round at all. But since we're adding and subtracting, as long as you get more than 2 decimal places, we're okay. You can get past that. 0.75 plus 0.0395, so 0.79. All right, so what does this mean? We are 99% confident that the probability a flu shot will be effective for a student selected at random is between 0.71 and 0.79. All right. Fortunately, I think the political polls have kind of been put on hold temporarily. Hopefully that's a blessing. It'll be interesting to see what happens once things start to settle down a bit. But interpreting results from a poll is an important subject when we talk about this. In most polls, the margin of error is given for a 95% confidence interval. So I would look up my Z for 0.95, and that would be the Z value I would use to calculate that confidence interval. So newspapers frequently report the results of an opinion poll. In articles that give more information, a statement about the margin of error accompanies the poll results. Oops, I went too fast. So it's the same calculation. It's not any different. It's just maybe understanding it in a little different way. So the margin of error is the maximum error of a 95% confidence interval for P. A 95% confidence interval for the population proportion is P hat minus the error, p hat plus the error. So it gives a range of values. Back when President Trump was elected, literally the day before the election, it was predicted that Hillary Clinton would win. But if you looked at the way the poll was reported, they were so close that the margin of error meant that really neither of them was ahead. So kind of interesting. I always will wonder if the media is saying, hey, she's gonna win, Hillary Clinton's gonna win. If people said, oh, I don't need to go vote because she's gonna win, perhaps that's why Trump won. Or maybe it got Trump supporters out there because they were like, no way is she gonna win. Hard telling. But so it's interesting, very often, it's really so close that the margin of error means that nobody's really ahead. Sample size. How do I know how big that sample size has to be? Okay, we looked at the fact that n times p has to be greater than 5, and, remember that's a test question, n times q has to be greater than 5. So both of those things have to be true in order to use this procedure. How do I know how big of a sample size I need? Okay, it depends on whether you have a preliminary estimate. So sometimes we have some information ahead of time. Maybe somebody did a slight study or they did a study on a similar situation, so we don't have to start from scratch. So this is really interesting to me. So we have two formulas, and again, these are on your formula sheet. So we have two formulas, n equals p times 1 minus p, z sub c over the error, square this, okay? That's an easy thing to forget, is to square that, if you have a preliminary estimate for p. If you do not, if you don't, so you'll notice this one actually includes p, right? And that's p, not p hat. But what if you do not have a preliminary estimate for p? You'll notice there's no p in this equation. So n is 1/4 z sub c, whatever our z sub c is, over the error, and that gets squared. What you'll notice in most cases, if we don't have a preliminary estimate, we have to have way bigger sample size, at least double typically. So interesting. So E is the maximum error of the estimate. Z sub c is that same critical value that we get off the table. So what if there is a company of selling wholesale popcorn to grocery stores? The company buys directly from farmers. A buyer for the company is examining a large amount of corn from a certain farmer. Before the purchase is made, the buyer wants to estimate P, the probability that a kernel will pop, right? He wants to make sure this is the good stuff that he's buying. Suppose a random sample of n kernels. So n is number of kernels. Now, just a little side note. If I was counting popcorn kernels, I wouldn't go 1, 2, 3. I'd have to have my tweezers out, right? No, I wouldn't count them that way. I would take several samples. Maybe I would count those. I would count how many were in that sample, and I would weigh several samples, and I would take an average and say, 1 pound of popcorn should have, I don't know, 1,000 kernels of corn in it. So you would use information as an estimate. Again, we're counting kernels of popcorn here. There's a little bit of room for margin of error. So the buyer wants to be 95% sure that the point estimate P hat equals R over N, for P will be in error either way by less than 0.01. So E is 0.01. My Z sub C, the C we want is 95. So I'll look that up on a Z chart, or on my little Z chart. If there is no preliminary study, I don't have any information, this is a new supplier, he hasn't been a farmer very long, I have nothing to go on. So here's my Z sub C chart, here's 0.95, so 1.96 is the Z I'm going to use. So my formula, N equals 1/4 Z sub C over the error quantity squared. So I'm going to substitute my values. So here's my z sub c, the 1.96. Here's my maximum error. So again, this might be the boss saying you can't be wrong by more than 0.01. And this is the probability that they're gonna pot. That's what this 0.01. So 1/4 is the same as 0.25. When they did this math, they came up with this. So 9,604. Ooh, so with no preliminary estimate, we'll need 9,604. That's a lot of kernels of popcorn. Let's see what happens if I have a preliminary estimate. And by the way, you never round down on this. This is one of these never round down. So a preliminary study showed that P was approximately 0.86. If the buyer uses the results of the preliminary study, how large of a sample should he use? So again, we have a P. We're going to use a little different formula. We have the same error. We have the same confidence, the same Z sub C, but we have a little different formula. So P times 1 minus P, Z sub C over the error. The Z sub C times over the error is squared. So 0.86, what is 1 minus P is 0.14. And same as that other formula. What we find is that it's 4,625.29. Again, we always round up, because if I didn't round up, I would either have a bigger error, this 0.01, or not be as confident. One or the other has got to give. So we want to make sure that this is, that we have this many, if I have some preliminary information. The first time we got 9,604, that's less than half. So sometimes it's worth doing a little bit of a preliminary study in order to have better information. All right, you guys have a great day. Keep the questions coming.